discussing rate laws, which yesterday we talked about how we can change the rates of reactions and what we can do with that. Well, now we're going to talk specifically about how can we figure out rate laws and how do they change, how do they progress for a reaction, okay? So it's dependent upon the reactant specifically. So however many reactants you have, they all need to be included in the rate law, okay? So for a reaction that's really simple, where you just have A going to B, so one reactant and one product, then the rate of the reaction is equal to the K times the concentration of A, okay? This is called a rate law. So anytime I tell you to determine the rate law, I want you to write something like this, okay? K is the rate law constant, or the rate constant, and it's specific for each reaction. We are not going to be solving for the K value today. We're going to be solving for the exponent that goes on the reactant, okay? But what I want you guys to make note of in your notes is that the brackets around your whatever your reactant is, the reactant, or the, sorry, maybe I have to delete this, oh well. The reactants brackets are equal to the concentration. There we go, I got it now. Okay, and so normally we're going to use molarity for the concentration, and so sometimes you might have to actually divide it out, and if I give you moles and I give you liters, and you have to divide it to plug in the number, but sometimes I give it to you because I'm nice. So we have to have concentration to plug in there. We're going to have rate values to plug into the rate sometimes, and we're going to write rate laws for reactions today. So the value of the rate constant K depends on the conditions of the reaction and is determined through experiment only, okay? That's a question answer on your packet. The value of the rate constant K in a rate law is really large if the products form quickly and very small if the products form slowly. So what that means is, if it's large, so I'm saying large is like when you have a number times 10 and it's like a positive exponent on the times 10, that means it's large. Like if it's times 10 to the positive 8 or positive 16 or something like that, that's large. And so that means that the products are favored. So that means there's actually going to be more products in the whole reaction vessel than reactants. But if you have a small number, so small as in when you have times 10, maybe it's to a negative exponent, like -3, -6, something like that. That's a really small number. Then that means that the products form slowly, or you can think of it as the reactants are favored, meaning the reactants don't want to react. They don't want to change into something else. Okay? That's an answer to another question in your packet. So there you go. So that's about K. We're going to talk about first order specifically, but we do have other orders in chemistry, or in AP chemistry. We have 0th order, first order, and second order. There's no such thing as third order. And we'll actually have to go into more detail all of these orders. But for us, we're just going to figure out the orders. So the order of a reaction is the power on which the concentration must be raised to from the experimental data. So it can only be found from experimental data, so you can only find it if you have a table full of data, okay? For a first order reaction, the rate is directly proportional to the concentration because it's going to have the exponent is just going to be a 1, okay? And so that this means that if they're directly proportional, then if the concentration of A is reduced by half, then the whole rate is reduced by half as well, okay? Higher order reactions, we do have those where we don't always just have one reactant. Like this is a double replacement reaction. The lowercase letters are the coefficients, and the uppercase letters are the actual reactants and products. But when you have more than one reactant, then the rate law is depicted with both reactants in brackets for their concentrations. And then notice how they have exponents x and y. And the reason why I put those letters in now is because, so yes, sometimes they do have the same exponent and sometimes they don't. And so we're going to have to actually solve for what those values are using the experimental data, okay? It's important to note here that you don't use the coefficients to know what the rate orders are, okay? The coefficients have nothing to do with the rate law. They're just there just because. Okay. So for our rate law, when each exponent equals 1, then we say it's first order A and first order B, because they both equal 1. The overall order of a reaction is adding up the exponents together. So if the x was 1 and the y was 1, then 1 plus 1 is 2. So the overall order for the whole thing is going to be 2. So we call it second order overall. We're not going to really do much with that. Do not assume that the coefficients are equal to the exponents, because they're not always the same. Just got to say that one more time. So we're going to do example 1 together, and then we'll pick one from the packet to do that's very similar to it. Okay? So, like, in every time that you have an example to do, or to do a problem, you are given a table with data. So, our equation for the reaction was A going to B, and the lowercase letters are just the coefficients, but they don't really matter, so it doesn't matter that we don't have numbers there, okay? We need to determine the rate law and determine the order of the reaction, okay? So the generic rate law, so if you don't know what the coefficients are going to be, we can write out still. So it's going to be rate is equal to K, our constant, times the concentration of the reactant. The products don't matter at all today, okay? So we're not thinking about the B, we're thinking about the A only. So in brackets, I'm going to put A, and then since I don't know what the order of the reaction is, I'm going to put an X for the exponent on the A, okay? So now, using the experimental data, we're going to solve what X is, okay? In order to solve what X is, we're actually going to take 2 trials. So notice trial 1, trial 2, trial 3. We have the concentration of A in each of them, and then we have the rate that the reaction takes place at from the experimental data. So when you have one reactant, it doesn't really matter which 2 lines you pick. When you have 2 reactants, it does definitely matter. Okay, so what 2 lines do you guys want to use today? 1 and 3? Okay, let's be difficult. I like it. Okay, so with 1 and 3, I always put it so that the rate, like the bigger numbers are on top and the smaller numbers on bottom. So for this one, to find X, I'm going to take, the rate of 3 is bigger than the rate of 1. So I'm going to take 3 versus 1. So what we're going to do is we're actually going to write out 2 rate law equations, plugging in the data from the table, and then solving, okay? So it's going to be 3 over 1. And that's just like to show what we're doing here, okay? So I'm going to take the rate from 3, which is 48 times 10 to the negative 4th. I know that that is not correct scientific notation, but it's just there so it shows you that math is easier. And then this rate of 1 is 3.0 times 10 to the negative 4. So what I'm doing here is I'm writing 2 equations. So the rate equals K times that for the top, the rate equals K times that for the bottom. So let's just keep going on the top. So next I have K, and then I need the concentration of A from the middle column, which for line 3, because we are doing 3 on top, is 0.2 raised to the X power, because I got to include that. And then on the bottom, I have K times the trial 1's concentration, 0.05. raised to the X power. Okay? Now that we have them both written out, what can cancel away? Because there's stuff that's on both the top and bottom, so they just cancel out. So what's canceling here? The K value is the same on both top and bottom, so we're just going to get rid of that. There's something else. The X has to stay, because we're solving for X. We can't cancel X out. The 10 to the negative 4th. It doesn't always work out that way, but it does on this problem. So I'm just going to take that away. So rewriting this, to simplify, I'm going to have 48 over 3 is equal to, and then have you guys done this in math before, where if they're both taken to the same power and you're dividing them, then you can simplify it by putting the fraction inside and then putting it to the power on the outside. Have you guys done that before? So I'm going to do that with 0.2 over 0.05. Okay? So this is helping us figure out how to solve for x. So now, can somebody take 48 divided by 3 and tell me what that is? Is it 16? Okay. And then that is equal to, let's reduce the inside, so it's 0.2 divided by 0.05. What is it? 4. Okay. So we have 16 is equal to 4 to the x power. I don't know how to do this on your calculator, but I just think about it logically, right? So like, we can start with the power of 0. What is something to the power of 0? What's that answer? 1. Anything to the power of 0 is 1. Well, that's not the case here. What if x was equal to 1? 4 to the first power, is that 16? No. What about 2? 4 squared is 16. So that means that x is equal to 2. What? Okay. So now this, we're going to rewrite the rate law, plugging in the 2 for the exponent instead of x. So rate is equal to k. We're just going to leave it a. We're not to plug any number in. Raised to the second power. Okay? And so then this is our first part of the answer for the example. But it also wants us to determine the order. So what order reaction is this? The order is dependent upon the exponent we just solved for. So it's second order because it has an exponent of 2. What do you say? Okay. And that's what we're going to do.